In 1906, a physicist in Duino, Italy, hanged himself while his daughter was swimming in the sea. His constant, the letter K, now appears in the most fundamental equation connecting information to heat. Why did Ludwig Boltzmann die believing his life's work had been rejected 2 years before the scientific community confirmed every word of it? In 2002, a team in Paris counted how many published medical facts from the last 50 years were still true. The answer was 60%. The rest had quietly become wrong, and the decay followed the exact same mathematical curve as radioactive uranium. And in 1900, sponge divers off a Greek island pulled a corroded lump of bronze from the seafloor. Inside it were precision-cut gears that should not have existed for another 1400 years. There is no record of anything like it before or after. These 3 stories have the same ending, and that ending is governed by a single line of physics that most scientists would rather not discuss, because what it says about the future of everything we know is something the equations have been clear about for decades. Get comfortable, settle in. If you are not subscribed, now is a good time, and for those of you who want to go even deeper across physics, history, collapse, and the mathematics underneath all of it, the Patreon is where that happens. Stay for this one, because by the end, you will understand why the knowledge you trust has an expiration date, and why the universe itself is the one enforcing it. Let's start where it started. In 2002, a team of researchers at the Pitié-Salpêtrière Hospital in Paris did something that nobody in medicine had ever thought to do before. They went back and checked. Not one paper, not 10, 474 original research articles on hepatitis and cirrhosis published between 1945 and 1999. More than half a century of accumulated medical knowledge, peer-reviewed, cited, taught in medical schools, used to treat patients. And they asked a question so obvious, it is almost embarrassing that nobody had asked it sooner. How much of this is still true? The lead researcher was a hepatologist named Thierry Poignard. He and his team had the Annals of Internal Medicine reassessed every single conclusion in those 474 papers against the best available evidence in the year 2000. And what they found should have made front-page news in every country on Earth. It did not. 285 of the conclusions, about 60%, were still considered true. 91, about 19%, had become obsolete, and 98 of them, just over 20%, were now considered outright false, not ambiguous, not debatable. False, published, peer-reviewed, cited, trusted, and wrong. But here is the part of Poignard's paper that nobody talks about. When you plot those numbers on a graph and fit them to a curve, the decay of medical truth does not look random. It does not scatter. It follows a clean, predictable, exponential decline, the same mathematical curve that describes the radioactive decay of uranium atoms. And Poignard calculated the half-life, 45 years. That is how long it takes for half of what medicine considers true in a given field to be proven false or obsolete. Not a metaphor, not an analogy. A measured, published number. The half-life of medical truth is 45 years. I want you to sit with that for a moment, because the implication is not that medicine made some mistakes a long time ago and has since gotten better. The implication is that right now, today, roughly half of what your doctor learned in medical school 2 decades ago has either been overturned or is in the process of being overturned. And neither your doctor nor you have any reliable way of knowing which half. And Poignard's study contained a detail that made the whole thing worse, a detail that his own team seemed almost reluctant to highlight. They broke the data down by methodology. Randomized controlled trials, the gold standard of evidence-based medicine, had a 20-year survival rate of 85%. Non-randomized studies, the ones everyone considers weaker, survived at 87%. But meta-analyses, the highest tier of the evidence pyramid, the methodology that is supposed to give you the most reliable answers by combining multiple studies into one, had a 20-year survival rate of 57%. The most rigorous methodology decayed the fastest. The thing designed to be most resistant to error was the most fragile. That result sat in a medical journal for years, and nobody outside of a very small circle of scientometricians seemed to notice. But one person did, a computational biologist at Harvard named Samuel Arbesman. And what Arbesman did with Poinard's finding was take it out of medicine and ask whether it applied everywhere. His 2012 book, The Half-Life of Facts, made an argument that should have restructured how every human being thinks about knowledge. He said that the decay of facts is not a failure of individual papers or individual scientists. It is a population-level phenomenon, just like a single uranium atom is unpredictable. But 1 billion uranium atoms have a precise, measurable half-life. A single fact might survive for centuries or be overturned next Tuesday. But a population of facts in any given field decays on a curve. And that curve is measurable. Arbesman called them mesofacts, facts that change on the timescale of a single human lifetime, not the hard constants like the speed of light or the gravitational constant, which holds steady across centuries, not the ephemeral facts like yesterday's weather or today's stock price, which nobody expects to last. Mesofacts are the ones in between, the ones you are taught in school as settled knowledge that quietly become wrong while you are still alive to remember learning them. And the examples are everywhere once you start looking. In 1923, a cytologist named Theophilus Painter at the University of Texas counted the number of chromosomes in human cells. He published the number 48, and for 33 years, every genetics textbook in the world printed that number, 48 chromosomes. It was taught, tested, memorized, and never questioned. Then, in 1956, Johan Tigeo and Albert Levin in Sweden published a paper with better staining techniques and a clearer preparation method. The actual number was 46. It had been 46 the entire time. For a third of a century, every biologist in the world had been carrying around a wrong number for one of the most basic facts about their own species. And here is the part that gets under your skin. Other cytologists had almost certainly counted 46 before Tigeo and Levin, but the published consensus said 48, so they assumed they had made an error. They adjusted their counts to match the accepted number. The wrong answer was so deeply embedded that correct observations were discarded as mistakes. That is not a story about one sloppy paper from the 1920s. That is a story about how knowledge systems work. The published record does not just reflect truth. It shapes what future observers are willing to see. And when the record is wrong, it actively prevents its own correction. Arbesman documented dozens of these. The Brontosaurus, which was reclassified as a Patasaurus in 1903, and then partially rehabilitated in 2015. Pluto, a planet for 76 years, and then not. The iron content of spinach, inflated by a decimal point error from 1870 that was not corrected until 1937. The number of taste regions on the tongue, which was never real and appeared in textbooks for decades because of a mistranslation of a German paper. each one a fact that millions of people learned, trusted, and repeated, that turned out to be wrong, not controversial, not cutting edge, just wrong. And Boltzmann went further. He pulled data from library systems and citation databases and found that scientific literature itself has a half-life. In physics, the half-life of a textbook in active use was roughly 13 years. In history, about 7, meaning half of all physics textbooks being actively consulted in any given year were published within the last 13 years. The other half had already been replaced. The knowledge did not accumulate like bricks in a wall. It rose, peaked, and decayed, like every radioactive isotope that has ever been measured. But this is where the story takes a turn that Boltzmann himself did not fully follow. Because if knowledge decays predictably, then the question is not whether we are losing knowledge right now. We are. The question is whether the decay follows a cycle, whether there is a pattern, whether civilizations build up knowledge, hit some kind of ceiling, and then lose it in a way that leaves a detectable signature. And the answer, which has been sitting in the data for over a decade, is yes, the cycle is real. The decay phase has a signature, and we are in it. I need to be precise about what I mean by that, because this is not a metaphor and it is not a warning about the future. This is a description of what the data already shows. And to see it clearly, you need to understand what happened when someone finally tried to check whether the entire scientific enterprise was producing reliable knowledge at all. The answer nearly ended several careers, and the people who fought hardest against it were the ones who had the most to lose. The year was 2005, and the man who pulled the pin was a Greek epidemiologist working at Stanford. His name was John Ioannidis, and he published a paper with a title so blunt it reads like an accusation: Why Most Published Research Findings Are False. It appeared in PLOS Medicine, and it has since become the single most accessed article in the history of the Public Library of Science. Not because people agreed with it, because they could not figure out how to make it wrong. Ioannidis did not run a single experiment for that paper. He did something more dangerous. He did math. He built a framework, a set of equations that calculated the probability that any given published research finding was actually true. And the inputs to those equations were not controversial. They were the known, accepted parameters of how science is actually conducted. The statistical power of typical studies, the ratio of true to false hypotheses being tested in a given field, the level of statistical significance required for publication, the flexibility researchers have in how they design, run, and analyze their experiments, the financial and career interests attached to positive results, and the competitive pressure in fields where many labs are chasing the same questions. When you plug the real numbers into Ioannidis' framework, what falls out the other end is devastating. For small studies with small effect sizes in hot fields with lots of competing groups, which describes a significant fraction of all biomedical research, the probability that a published finding is true drops below 50%. For some configurations, well below. And Ioannidis did not hedge. He wrote, and I am giving you his exact words because you deserve to read them. It can be proven that most claimed research findings are false. Not might be, not could be, can be proven. He laid out 6 corollaries, each one worse than the last. The smaller the studies in a field, the less likely the findings are true. The smaller the effect sizes, the less likely. The more relationships tested in a study, the less likely. The more flexibility in design and analysis, the less likely. The greater the financial and career interests, the less likely. And the hotter the field, the more competition, the more groups racing to publish, the less likely any individual finding is true. He describes science as a system with a built-in false positive accumulation rate that increases the more productive and competitive the enterprise becomes. Growth itself was the engine of decay. Now, you might think the scientific community absorbed this, course-corrected, and moved on. It did not. What happened instead was a decade of something that has come to be called the replication crisis, and the numbers that emerged from it are worse than what Ioannidis predicted. In 2015, a group called the Open Science Collaboration, led by Brian Nosek at the University of Virginia, published the results of the largest systematic attempt to reproduce published psychological research ever conducted. It appeared in Science, one of the two most prestigious journals on Earth. They took 100 studies from 3 top psychology journals, studies that had been published in 2008, and they attempted to replicate each one. These were not obscure papers from marginal journals. These were the flagship results of the field. In the original papers, 97% of the results were statistically significant. That is what you would expect. Journals publish positive results. The system selects for significance. But when the replication team ran the same experiments again, with the same methods, the same statistical tests, and often larger sample sizes, the significance rate dropped to 36%, from 97 to 36. And the effect sizes, the actual magnitude of the results, were on average half of what the originals reported. Half. The flagship results of an entire field halved on replication. That is not a rounding error. That is a discipline, discovering that most of what it published in its best journals in a given year does not hold up when someone else tries to do it again. But psychology was not the worst. In 2012, 3 years before the Open Science Collaboration published, a team of scientists at Amgen, the biotech company, published a short letter in Nature that is still one of the most quietly devastating documents in the history of science. Glenn Begley and Lee Ellis reported that Amgen's internal team had spent a decade trying to reproduce 53 landmark cancer biology papers. These were not random papers. These were the papers that other scientists cited when justifying entire research programs. The papers that influenced which drugs got developed, which clinical trials got funded, which patients got treated. Amgen could confirm the findings in 6 of them. 6 out of 53, an 11% success rate. And Amgen would not say which papers failed, citing confidentiality agreements, which means the 47 papers that could not be reproduced are still sitting in the literature right now, still being cited, still influencing research directions and clinical decisions, and nobody outside of Amgen knows which ones they are. Bayer ran a parallel assessment. Their team, led by Florian Prinz, published in Nature Reviews Drug Discovery in 2011. They reported that they could reproduce published findings in roughly 25% of cases. 1 in 4. I want to be clear about what these numbers mean in aggregate. This is not about individual bad actors or individual bad papers. This is about the base rate of truth in the published scientific record. The system that generates what we call knowledge has a measurable false positive rate, and that rate is not 5%, which is what the standard statistical threshold of p less than 0.05 would suggest. It is somewhere between 50 and 89% in the fields where anyone has actually checked. In 2016, Nature, the journal, published its own survey. Monia Baker surveyed 1,576 scientists across disciplines. More than 70% reported that they had tried and failed to reproduce another scientist's published experiments. More than half reported that they had failed to reproduce their own. When asked whether science was experiencing a reproducibility crisis, 52% said yes, there is a significant crisis. And even the respondents who did not call it a crisis had numbers that supported one. In chemistry, 87% of researchers had tried and failed to reproduce someone else's work. In biology, 77%. In physics and engineering, 69%. In medicine, 67%. Think about that for a moment. In physics, a field that prides itself on precision, rigor, and the hardest standards of evidence in all of science, 7 out of 10 researchers admitted in an anonymous survey that they had tried to reproduce a published result and could not. And here is the detail from Baker's survey that should genuinely unsettle you. Despite these numbers, fewer than 31% of the respondents believed that failure to reproduce a result meant the original result was probably wrong. The majority of working scientists, confronted with evidence that published results routinely fail replication, did not conclude that the results were unreliable. They concluded that replication is hard, that conditions are difficult to match, that failure to reproduce does not necessarily invalidate the original. The system had built a defense mechanism against its own quality control. The decay was not being denied, it was being rationalized. Ioannidis had seen this coming. In his original 2005 paper, he included a passage that reads, "Like prophecy now." He wrote that for many current scientific fields, claimed research findings may often be simply accurate measures of the prevailing bias, not truth, not approximations of truth, accurate measures of bias. The machine was not discovering reality. It was measuring its own assumptions and publishing them as facts. Now, here is where it would be tempting to treat this as a modern problem, a consequence of publish or perish culture, of perverse incentives, of the sheer volume of papers being produced in the 21st century. And those factors are real. Global scientific output is doubling approximately every 9 years. According to a 2015 analysis by Lutz Bornmann and Rüdiger Mutz in the Journal of the American Society for Information Science and Technology, we are producing more published knowledge per year than at any point in human history. But the decay rate per individual contribution is accelerating at the same time. More papers, faster obsolescence, lower replication rates. The growth and the decay are not independent, they are coupled. The faster the system produces, the faster it forgets. And if you think that sounds like a thermodynamic process, you are not wrong. But that connection, which is where this story ultimately goes, requires you to understand something else first, something about what happens to knowledge after it gets published. Because the replication crisis is about truth. What comes next is about memory. And memory, it turns out, dies on a different schedule, one that has been measured just as precisely and ignored just as thoroughly. Ioannidis was not some outsider lobbing grenades at the establishment. He trained at Harvard Medical School. He held positions at Tufts, at Johns Hopkins, at the University of Ioannina in Greece, and eventually at Stanford, where he became co-director of the Meta Research Innovation Center. He was inside the system at the highest levels, and he used the system's own tools to demonstrate that the system was broken. And the reaction was exactly what you would predict from everything I have told you about how institutions handle uncomfortable truths. Some researchers engaged with the paper seriously. Stephen Goodman and Sander Greenland published a critique in PLOS Medicine in 2007, arguing that parts of Ioannidis' mathematical framework were circular, that certain assumptions were baked in that guaranteed the pessimistic conclusion. And they had a point, technically. But the empirical data that arrived in the following decade made the technical objections irrelevant, because it turned out Ioannidis was not pessimistic enough. The actual replication rates, when people finally started checking, were worse than his model predicted. And there was a deeper irony that Ioannidis himself pointed out. The reaction to his paper was, in many cases, itself an illustration of the problem he was describing. Researchers who criticized his framework often did so using the same statistical methods that his paper had shown to be unreliable. They were using the broken tool to argue that the tool was not broken. Leake and Jagger published a 2014 analysis in Biostatistics, estimating that the empirical false positive rate in biomedical literature was around 14%, much lower than Ioannidis' theoretical prediction. But 14% is still catastrophic. If 1 in 7 published findings in medicine is wrong, and there are approximately 2 million biomedical papers published per year, that is roughly 280,000 false results entering the medical literature annually. 280,000, each one potentially influencing clinical decisions, drug development pipelines, treatment protocols, each one a fact that some doctor somewhere is relying on to help a patient. And the crisis was not limited to medicine. In 2010, a social psychologist named Darrell Bem at Cornell published a paper in the Journal of Personality and Social Psychology, claiming experimental evidence for precognition, the ability to perceive future events. The paper passed peer review at one of psychology's flagship journals. It used standard statistical methods, it met the conventional threshold for significance, and it concluded that human subjects could perceive stimuli that had not yet been presented to them. The reaction within psychology was not primarily about whether precognition was real. It was about what the paper revealed, about the methods themselves. If standard statistical methods and standard peer review at a top journal could produce a published paper claiming evidence for psychic powers, then either psychic powers were real or the methods were fundamentally insufficient to distinguish true results from false ones. And since almost nobody in the scientific establishment was willing to accept precognition, the implication was that the methods were the problem. The same methods used in every other paper in the same journal. The same methods that had generated the entire published knowledge base of social psychology. Bem's paper did not prove precognition. It proved that the evidentiary standards of an entire field could not reliably distinguish a real effect from a phantom one. And that is a different kind of decay. Not the decay of a specific fact, but the decay of the system's ability to distinguish fact from noise. The instrument was drifting out of calibration, and nobody had checked the calibration in decades. There was a response. Eventually, the open science movement, pre-registration of studies, registered reports, data sharing mandates, these are real and they matter. But they are retrofits on a system that spent decades accumulating a published record whose reliability is genuinely unknown. The papers that were already published under the old system, the millions of them, are still in the literature, still being cited, still informing research and clinical practice. And nobody is going back to check all of them. Nobody can. The volume is too large, the cost too high, the incentives too weak. The decay has already happened. What is in the literature is in the literature, and some significant fraction of it, somewhere between 14 and 50%, depending on whose estimates you trust and which field you are looking at, is wrong. And this is where the half-life metaphor becomes more than a metaphor, because in radioactive decay, you do not know which specific atom will decay next, but you know exactly how many atoms will have decayed after a given period. The same is true of the scientific literature. We do not know which specific papers are wrong, but we can calculate with uncomfortable precision approximately how many of them are wrong. And that number is not small, and it is not shrinking. There is a man you have almost certainly never heard of who is responsible for the fact that we can measure any of this. His name was Derek John de Soller Price, and he was born in Leighton, England in 1922. His father was a tailor. His mother was a singer. He trained as a physicist and then as a historian of science, which made him an outsider in both fields. And in 1963, at Yale, he published a book that invented an entire discipline out of thin air. It was called Little Science, Big Science, and it was the first systematic attempt to treat scientific knowledge itself as a measurable, quantifiable phenomenon. The way a physicist measures the properties of atoms, de Soller Price measured the properties of science. What he found was disturbing even then. The number of scientific journals had been growing exponentially since the Philosophical Transactions of the Royal Society was founded in 1665, doubling every 15 years. The number of scientists was growing exponentially. The number of papers was growing exponentially. Everything about the production of knowledge was on an exponential curve. And de Soller Price asked the obvious question that nobody wanted to hear. Exponential growth cannot continue forever in a finite system. At some point, the curve saturates. And when it saturates, what happens? He introduced a concept that is still used today, the citation half-life, the time period during which half of all currently cited papers in a field were published. If the citation half-life of a field is 10 years, it means that half the papers being cited this year were published in the last decade, and the other half are older than 10 years. Anything beyond the half-life is sliding toward oblivion, still accessible in principle, still in the library, but functionally dead, uncited, unread, unfound. A 2015 analysis by Alex Verstack and colleagues, published on Arxiv, measured citation half-lives across thousands of journals. The mean cited half-life for newer journals was 5.1 years. For older, more established journals, 7.1 years. Those numbers mean that in the average scientific field, half of all actively cited papers become functionally invisible within 5 to 7 years of publication. And here is the counterintuitive finding. The half-lives are getting longer, not shorter. They have been growing by roughly 0.13 to 0.19 years per year since the 1960s. You would expect the digital age to accelerate obsolescence. More papers, more competition for attention, faster turnover. But the opposite is happening. Papers are staying in active citation slightly longer than they used to. And the reason turns out to be precisely what makes the decay so insidious. Digital search does not fight the decay. It concentrates citations on a smaller number of older papers, while the long tail dies faster. The rich get richer. The forgotten get more forgotten. The average goes up because the distribution gets more unequal. But citation decay is only the visible part of what happens to knowledge after it enters the record. There is a second, deeper form of death that is far harder to detect, and a sociologist named Robert K. Merton identified it in 1949. He called it obliteration by incorporation. Merton was at Columbia, and he was studying how ideas move through scientific communities, and he noticed something that did not fit the standard model of scientific progress. When an idea first appears, it gets cited heavily. People refer back to the original paper, the original author, the original formulation. But if the idea is successful, if it becomes widely accepted and deeply embedded in the field, something strange happens. The citations start to drop. Not because the idea is being rejected, because it is being absorbed. it becomes so fundamental, so taken for granted, that people stop attributing it. It becomes invisible by virtue of its own success. Merton wrote, and again I want to give you his exact words, "The sources of an idea, finding or concept become obliterated by incorporation in canonical knowledge, so that only a few are still aware of their parentage. The more important the idea, the more completely its origin is erased." Watson and Crick's 1953 paper on the structure of DNA is now rarely cited explicitly in genetics papers, not because it was wrong, because it was so right that it became the water the entire field swims in. Einstein's 1905 papers on special relativity and the photoelectric effect are almost never cited in modern physics papers. The ideas are everywhere. The attribution is gone. Think about what that means for the knowledge cycle. At the surface level, citation counts. The visible layer, knowledge appears to decay as papers stop being cited. But underneath, some of that knowledge has not actually been lost. It has been obliterated by incorporation. It is still there, embedded in the foundations, unnamed and unattributed. And the critical problem is that you cannot tell the difference from the outside. A paper that stopped being cited because it was wrong looks identical in the citation record to a paper that stopped being cited because it was so important that it became invisible. The decay signature of failure and the decay signature of total success are the same curve. Merton also identified the inverse, a phenomenon he called adumbrationism, the tendency to retroactively attribute ideas to earlier sources that never actually contain them. People would read current knowledge back into historical texts, finding precursors and anticipations that the original authors never intended. Knowledge that did not exist gets credited to people who did not discover it, while actual discoverers get obliterated. The historical record of who knew what and when becomes, over enough time, unreliable. And this is where de Solla Price's career becomes the story itself. Because the man who invented the tools to measure the decay of knowledge spent the other half of his career trying to rescue one of the most spectacular examples of knowledge loss in human history. In 1900, sponge divers working off the coast of the tiny Greek island of Antikythera, under the direction of Captain Dimitrios Kontos, pulled up artifacts from a Roman shipwreck. Among the bronze statues and marble fragments was a corroded lump of metal about the size of a large dictionary. Nobody paid much attention to it. It was catalogued and placed in storage at the National Archaeological Museum in Athens. Then, on May 17, 1902, an archaeologist named Valerios Stais was examining the recovered objects and noticed that the corroded lump contained what appeared to be a gear wheel, a precision-cut, toothed gear wheel, inside an artifact that had been sitting on the seafloor since roughly the 1st century before the Common Era. This made no sense. The ancient Greeks were not supposed to have gears, not like this, not precision machined gears arranged in a complex interlocking mechanism, and for decades, nobody could figure out what it was. It was de Solla Price who took the mechanism seriously. In 1959, he published an analysis in Scientific American, arguing that this was a computational device, an analog computer designed to calculate the positions of the sun, moon, and planets, to track eclipse cycles, and to model the irregular motion of the moon using a sophisticated gear train. His 1974 monograph, Gears from the Greeks, laid out the technical reconstruction in detail. He was right. In 2005, a team using microfocus X-ray, computed tomography, the Antikythera Mechanism Research Project, led by Tony Freeth, decoded more than 3,500 words of inscription on the internal surfaces of the mechanism. The current dating places it between 200 and 5 and 60 before the Common Era. It contains at least 30 meshing bronze gears. It models the Metonic cycle, the Saros eclipse cycle, and the irregular elliptical orbit of the Moon using a pin and slot mechanism that is mathematically equivalent to Kepler's second law, derived 17 centuries later. Nothing of comparable mechanical complexity appears anywhere in the archaeological record until the astronomical clocks of 14th century Europe. That is a gap of roughly 1400 years, 14 centuries during which humanity possessed no device as sophisticated as what Greek craftsmen built before the birth of Christ, and there are no archaeological intermediates, no simpler versions leading up to it, no successor devices leading away from it. It appears in the record, fully formed, and then it vanishes, as though someone had worked out an entire tradition of precision mechanical computation, and then the tradition simply stopped. The Solar Price died of a heart attack in 1983. He was 61. He did not live to see the X-ray tomography work that confirmed his reconstruction. He did not live to see the inscriptions decoded. He did not live to see the discipline he invented. Scientometrics produced the data that proved knowledge decays on a measurable curve. The man who saved the Antikythera mechanism from obscurity and who invented the tools to measure knowledge death did not survive to see either project completed. And the mechanism itself sits in Athens, behind glass, corroded and fragmentary, as a monument to a fact that the modern world would rather not think about. Advanced knowledge does not just accumulate, it can be lost so completely that 1400 years pass before anyone builds anything comparable. And we only know it existed at all because a Roman cargo ship happened to sink in a spot where sponge divers happened to work 2,000 years later. But here is where this stops being a story about the ancient world and starts being a story about you. Because the digital infrastructure that stores modern scientific knowledge is not 14 centuries old. It is not 14 decades old. A web page, on average, lasts about 100 days before it is significantly changed or removed. That figure comes from Brewster Kahle, the founder of the Internet Archive, corroborated by a 2000 study from Alexa Internet. 100 days, the entire sum of human knowledge published on the Internet, has a half-life measured in months. In 2014, Martin Klein and colleagues published a paper in PLOS ONE titled Scholarly Context Not Found. They analyzed URI references in 3 major journal corpora and found that 1 in 5 articles, 20%, suffered from what they called reference rot. The links to supporting data, supplementary materials, and cited online sources were dead, gone. The papers still existed, but the evidence they pointed to had vanished. A 2016 follow-up by Jones and colleagues found that 75% of URI references led to content that had drifted from the version originally cited, not deleted, changed. The knowledge was still there in name, but the thing it pointed to had become something else. And the physical infrastructure is no better. NASA spent years in the 2000s trying to reconstruct data from its 1960s lunar telemetry tapes. The tape existed, but the tape drives capable of reading them had been scrapped decades earlier. The format was extinct. The knowledge was there, physically encoded on magnetic strips and functionally inaccessible because the machine that could translate it had been destroyed. The Antikythera mechanism lost 1400 years because the civilization that built it collapsed. NASA's lunar data nearly lost decades because someone threw away the tape drives. The mechanism of erasure was different. The result was the same. And the question that no one is asking, or at least not asking loudly enough, is whether there is a common pattern underneath all of it. Whether knowledge loss follows a predictable structure, not just in the details of what is lost, but in the shape of the loss itself. There is a book that nearly every educated person has heard of, and almost nobody has actually read. It was published in 1962 by a physicist turned historian named Thomas Samuel Kuhn. It was called The Structure of Scientific Revolutions, and it proposed something that the scientific establishment found deeply offensive. Kuhn said that science does not progress in a straight line. It does not accumulate truths the way a mason lays bricks. Instead, it follows a cycle. And the cycle has phases that repeat, and one of those phases involves the destruction of knowledge that came before. Kuhn described 5 stages. The first is pre-paradigm science, a chaotic period where there is no shared framework, no agreement on methods, no consensus on what even counts as a legitimate question. Then a paradigm emerges, a framework so compelling that it unifies the field. This inaugurates what Kuhn called normal science, the second stage. During normal science, researchers do not question the paradigm. They solve puzzles within it. They refine measurements, extend applications, fill in details. This is what most working scientists do for their entire careers. It is productive, valuable, and stable. But anomalies accumulate, results that do not fit the paradigm, experiments that produce numbers the framework cannot explain. At first, these are set aside, treated as noise, experimental error, things to be resolved later. But over time, they pile up, and when enough anomalies accumulate, when enough unexplained results stack high enough, the field enters what Kuhn called crisis, the third stage. During crisis, the rules loosen. People start questioning the fundamentals. Competing frameworks emerge. The unity of normal science fractures. And then, if conditions are right, revolution. The fourth stage, a new paradigm replaces the old one, not by proving the old one wrong within its own framework, because that is precisely what Kuhn argued is impossible. The new paradigm does not answer the old paradigm's questions. It replaces the questions themselves. What counted as a legitimate problem under the old paradigm becomes meaningless or irrelevant under the new one. The two frameworks are, in Kuhn's famous word, incommensurable. They cannot be translated into each other. And this incommensurability means that something is always lost in the transition. Kuhn called this Kuhn loss, and it is the part of his theory that the scientific establishment has spent 60 years trying to pretend does not exist. In every paradigm shift, some of the explanatory power of the old framework is permanently abandoned, not because it was wrong in every respect, but because the new framework does not need it, does not value it, and eventually does not remember it. Phlogiston theory is the textbook example that gets trotted out to make this sound trivial. Before oxygen was discovered, chemists explained combustion through phlogiston, a substance released during burning. When Lavoisier replaced phlogiston with oxygen in the 1780s, phlogiston's explanatory apparatus was abandoned, and nobody misses it, because oxygen chemistry is so much more powerful and accurate that the loss is invisible. But that is the sanitized version. The real examples are harder to dismiss. Ptolemaic astronomy, with its epicycles and deferents, could predict planetary positions with remarkable accuracy. When Copernicus replaced geocentrism with heliocentrism in 1543, his system was initially worse at prediction than Ptolemy's. The old model's detailed positional accuracy was a form of knowledge that was lost in the transition and not recovered until Kepler introduced elliptical orbits in 1609, 66 years later. For 6 decades, astronomy had less practical predictive power than it had under the old paradigm. That is not progress. That is a temporary regression in functional capability during a transition between knowledge systems. Caloric theory, which treated heat as a fluid, produced intuitions about heat flow that were useful and productive and that were abandoned when the kinetic theory of heat replaced it. The specific knowledge of how to think about heat transfer in fluid terms, the engineering heuristics built on caloric theory, decayed. Some were eventually reconstructed in the new framework. Some were not. And Kuhn identified something else that the establishment hated even more than Kuhn loss. He observed that paradigms do not die because they are refuted. They die because their adherents die. The physicists who committed their careers to the old paradigm do not switch to the new one. They retire, they pass away, and a new generation grows up inside the new framework, never having learned the old one, never knowing what was lost. Max Planck said it most bluntly, and Kuhn quoted him. A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that is familiar with it. Science advances one funeral at a time. Now, I need to show you what this looks like at civilizational scale, because Kuhn was talking about shifts within a continuous scientific tradition. What happens when the tradition itself breaks is orders of magnitude worse. And it has happened, repeatedly, with a signature that is now recognizable. Around 1200 before the Common Era, something destroyed virtually every major civilization in the Eastern Mediterranean within a span of roughly 50 years. The Mycenaeans, the Hittites, the Egyptians of the New Kingdom, the city-states of Ugarit and Al-Alaq, the Kassite dynasty in Babylon. All of them collapsed or were severely diminished in a single catastrophic period that historians now call the Bronze Age collapse. Eric Klein, in his 2014 book 1177 BC, The Year Civilization Collapsed, argues that no single cause can explain it. Drought, famine, the mysterious sea peoples, an earthquake storm that struck a tectonic chain from Greece to the Levant, and the cascading failure of the international trade networks that connected all these civilizations into a single interdependent system. When the network failed, they all fell. But the knowledge loss is what makes the collapse relevant here. The Mycenaean Greeks used a writing system called Linear B. It was a syllabic script used for palace administration, inventory, taxation, religious offerings. When the palaces burned, the scribes died or scattered, and Linear B vanished from human use. Completely. No one on earth could read it. No one knew what language it recorded. It had been a living writing system used by a sophisticated civilization, and it became a series of indecipherable marks on clay tablets for 3,100 years. It took until 1952 for a man to crack it. His name was Michael Ventris, and he was not a linguist. He was an architect. He had been obsessed with Linear B since the age of 14, when he attended a lecture at the Royal Institution in London given by Sir Arthur Evans, the excavator of Knossos. Ventris spent years working on the decipherment in his spare time, corresponding with professional classicists who were mostly skeptical that an amateur could succeed. And on June 1st, 1952, working with a grid-based substitution method and testing against newly discovered tablets from Pylos, he realized that Linear B recorded an early form of Greek, Mycenaean Greek, a discovery that rewrote the history of the Greek language and proved that Greek civilization was centuries older than anyone had believed. Ventris was 30 years old. He collaborated with the Cambridge philologist John Chadwick to publish documents in Mycenaean Greek the definitive account of the decipherment. And on September 6, 1956, hours after delivering the final manuscript to his publisher, Ventris was killed in a car crash on the Great North Road near Hatfield. He was 34. The man who ended a 3,100-year silence died 4 years after breaking it. Chadwick finished the book alone, and the knowledge that was recovered is devastating in its mundanity. Linear B tablets are mostly inventories, livestock counts, grain stores, offerings to gods, tax records. The writing system of an entire civilization preserved almost nothing of its literature, its myths, its science, its accumulated understanding of the world. All of that was transmitted orally or on perishable materials. When the palaces burned, the administrative records survived because they were baked clay. Everything else was gone. Klein has a line about this that I keep coming back to. He wrote that since only the top 1% of the population could read or write, they lost that ability after the collapse. It took centuries for writing to return to Greece, and only after the Phoenicians brought their alphabet, centuries, an entire civilization went from literate to illiterate, and stayed that way for generations. The knowledge graph did not dip. It cratered, and the Bronze Age collapse is not even the most instructive example, because what happened with Aristarchus of Samos is in some ways worse. Aristarchus lived around 310 to 230 before the Common Era. He was a mathematician and astronomer on the island of Samos, and he proposed that the Earth rotates on its axis and orbits the Sun. Heliocentrism, 1700 years before Copernicus. We know this because Archimedes mentioned it in a work called The Sand Reckoner. Aristarchus's own treatise on heliocentric astronomy did not survive. It is lost. We have his calculations of the relative sizes and distances of the Sun and Moon, which survive in a separate work, but the heliocentric theory itself exists only as a reference in someone else's book. And the response to Aristarchus at the time was not indifference, it was hostility. The Stoic philosopher Cleanthes reportedly wrote that Aristarchus should be indicted for impiety for putting the half of the universe in motion. The charge against him was not that he was wrong, it was that his idea was offensive to the established order. What followed was 1800 years of geocentrism. Aristotle's authority, Ptolemy's detailed mathematical model in the Almagest, and the weight of cultural and religious tradition kept the Earth at the center of the universe for nearly 2 millennia. And when Copernicus finally proposed heliocentrism again in 1543, he knew about Aristarchus. He cited Aristarchus by name in an early draft of De Revolutionibus, and then he removed the reference before publication. The man who reintroduced heliocentrism to the world deliberately erased the name of the man who had discovered it 18 centuries earlier. That is not just knowledge loss. That is knowledge loss compounded by deliberate obliteration of the historical record. Copernicus did not want his idea to be seen as a revival of an ancient heresy. He wanted it to be new. And so Aristarchus, who was right about the most fundamental fact of planetary astronomy, was forgotten for so long that when his idea finally returned, even the person who brought it back chose to pretend it had never existed. And the pattern repeats. Roman concrete, Damascus steel, Greek fire, the Antikythera mechanism. Each one represents advanced technical knowledge that was lost completely and took centuries to partially recover, if it has been recovered at all. Roman opus caementicium, the concrete used in the Pantheon and in harbour structures that have survived 2,000 years of saltwater exposure, was not fully understood until January 2023. That is when Admiral Masick and colleagues at MIT and Harvard published a paper in Science Advances titled Hot Mixing. mechanistic insights into the durability of ancient Roman concrete. They discovered that the Romans mixed quicklime directly with pozzolanic ash at high temperatures, a process called hot mixing, which produced calcium-rich lime clasts throughout the concrete. When cracks form, water infiltrates, dissolves the lime clasts, and recrystallizes as calcium carbonate, sealing the crack. The concrete heals itself, and the specific mechanism was different from what Vitruvius described in De Architecture around 30 before the Common Era. Even the Roman technical literature did not fully capture how the process worked. The tacit knowledge of the builders exceeded what the writers could record. Damascus steel, or Wootz steel, was produced from crucible steel originating in South Asia. The blades had a characteristic banding pattern of carbide nanotubes that gave them extraordinary hardness and edge retention. The tradition collapsed in the late 18th century when colonial restructuring disrupted the supply of specific iron ores from southern India. In 1998, John Verhoeven and Alfred Pendray at Iowa State University published in JOM, the Journal of the Minerals, Metals, and Materials Society, that the key to the microstructure was trace impurities of vanadium at concentrations down to 40 parts per million. 40 parts per million. No Western smith would have suspected that an impurity at that concentration mattered. And even Verhoeven and Pendray could only reproduce the microstructure and appearance. The full working knowledge, the smith's feel for the color of the metal at the right moment, the sequence of heating and folding, the judgment calls made in real time, is gone. That knowledge was embodied in living practitioners, and when the last practitioner died, it died with them. Greek fire was the Byzantine Empire's secret weapon. Attributed to a Syrian engineer named Kallinikos of Heliopolis around 1672, it was a liquid incendiary that could burn on water. It was deployed through bronze siphons mounted on ships, and it was decisive in repelling Arab sieges of Constantinople in 1608 and 17 to 718. The recipe was so closely guarded that it was compartmentalized. No single person outside the imperial family knew the full formula. When the Bulgarians captured 36 siphons and quantities of the substance in 814, they could make no use of them because the operators only knew their own compartmentalized step. The full recipe was lost within roughly 50 years of its invention and remains unrecovered today. Each of these represents a different mechanism of knowledge death, but the pattern underneath is the same. Knowledge that was held by a civilization was lost when the conditions that sustained it changed. The trade networks that supplied the right iron ore, the living tradition of concrete mixing, the compartmentalized recipe of an incendiary weapon, the scribes who could read a syllabic script. In every case, the knowledge was not disproven. It was not superseded by something better. It was simply dropped. The civilization stopped paying the cost of maintaining it, and it vanished. And if you need further proof that knowledge decay is the default state and preservation is the exception, consider the route by which the ancient Greek intellectual tradition survived into the modern world. It did not survive in Greece. It did not survive in Rome. It survived because a civilization most Westerners know almost nothing about spent 3 centuries deliberately, systematically translating and preserving texts that Europe had allowed to rot. The Islamic Golden Age, running roughly from the 8th through the 13th centuries, was one of the most consequential intellectual projects in human history, and its most important institution was the House of Wisdom in Baghdad, founded under the Abbasid Caliphate. Under Caliph al-Ma'mun, who ruled from 813 to 833, the House of Wisdom became the center of a deliberate translation movement. Scholars were dispatched across the former territories of the Byzantine and Persian empires to find Greek manuscripts, and teams of translators, including the legendary Hunayn ibn Ishaq, rendered them into Arabic. Ptolemy's Almagest, the geocentric astronomical masterwork that had replaced Aristarchus's heliocentrism, survived into Western Europe only through Arabic. The very name Almagest is not Greek, it is Arabic. Al-Majisti, a corruption of the Greek Megister, meaning the greatest. The book that codified geocentrism and buried heliocentrism for 18 centuries reached Europe wearing an Arabic name, because Arabic-speaking scholars were the ones who preserved it, when Greek-speaking and Latin-speaking civilizations let it decay. Muhammad ibn Musa al-Khwarizmi, working in Baghdad around 820, wrote a treatise on solving equations that gave the world two words: algebra, from the Arabic al-jabar meaning restoration, and algorithm, a Latinization of his own name. These are not peripheral contributions. They are the foundational vocabulary of modern mathematics and computer science, and they reached Europe through the translation efforts of the 12th century school of Toledo, where Arabic texts were rendered into Latin and became the curriculum of the first European universities. This means that the intellectual tradition that the modern West considers its heritage, the line from Euclid to Newton to Einstein, has a break in it. A centuries-long break, during which the transmission line ran not through Christian Europe, but through Islamic Baghdad, Cordoba, and Cairo. The knowledge survived the decay phase of one civilization only because another civilization was in its accumulation phase at the right time and had the institutional will to absorb and preserve what the first had abandoned. And even with all that preservation, the losses were staggering. The Library of Alexandria, the most famous case of knowledge destruction in popular culture, is actually less straightforward than most people realize. It was not destroyed in a single dramatic fire. Modern scholarship, particularly from Roger Bagnall and others, suggests the loss was distributed across multiple events. Julius Caesar's fire in 48 before the Common Era, which Seneca, citing Livy, says destroyed 40,000 scrolls. The destruction under the Roman Emperor Aurelian around 273. The demolition of the Serapeum, the daughter library under Bishop Theophilus in 391, and the gradual neglect following the Arab conquest in 642. But the most devastating cause of loss may have been the quietest. Around the 3rd and 4th centuries, the technology for storing text shifted from scroll to codex. Any text that was not transferred from scroll to codex format during this transition was effectively sentenced to death. Scrolls degrade. They require recopying to survive. And the decision about which texts to recopy was made by individuals and institutions with finite resources and specific priorities. Religious texts were copied. Philosophical texts that were compatible with the new religious order were copied. Scientific and mathematical texts were copied if they had powerful patrons or institutional support. Everything else was left to decay. The great bulk of ancient literature, estimates suggest that fewer than 1% of ancient Greek literary works survive in any form, was not burned or destroyed. It was simply not copied. The maintenance cost was not paid, and the second law collected. Consider Eratosthenes, around 240 before the Common Era. Working as the chief librarian at Alexandria, he calculated the circumference of the earth. His method was elegant. He knew that at noon on the summer solstice, the sun was directly overhead in Syene, modern Aswan, because sunlight reached the bottom of a deep well there without casting a shadow. At the same moment in Alexandria, roughly 800 kilometers to the north, a vertical stick cast a shadow indicating that the sun was about 7 degrees off vertical. 7 degrees is approximately 1/50th of a full circle. Therefore, the circumference of the Earth was approximately 50 times the distance from Syene to Alexandria. His result, depending on which value you assign to the stadion he used, was accurate to within roughly 2 to 16% of the true value. That was 240 years before Christ. And when Columbus sailed in 1492, 1732 years later, he was working with a number for the Earth's circumference that was about 25% too small. He had conflated an Arabic estimate based on a different unit of measurement with Italian miles, producing a figure for the distance from Europe to Asia that was dramatically wrong. Columbus believed the westward journey to Asia was about 3,700 kilometers. The actual distance is over 19,000. If the Americas had not happened to be in the way, his crew would have died at sea. This is not a charming historical anecdote. This is numerical knowledge regression. Eratosthenes had a better number in 240 BC than Columbus had in 1492 AD. The knowledge did not accumulate. It degraded, and the degradation nearly proved fatal. I want to pause here and map the shape of what I have just shown you, because the individual examples, the chromosome count, the replication crisis, the citation half-lives, the Antikythera mechanism, Aristarchus, Roman concrete, Damascus steel, Eratosthenes, the Library of Alexandria. Each one of these is usually presented as a separate historical curiosity, an interesting but isolated case. That framing is wrong. They are not isolated. They are data points on the same curve. The curve has 3 features. First, a growth phase. Knowledge accumulates exponentially, driven by institutional support, communication networks, and the self-reinforcing nature of puzzle solving within a paradigm. Second, a saturation phase. Growth slows as the paradigm encounters anomalies, as institutional overhead increases, as the cost of maintaining the accumulated knowledge base begins to compete with the cost of producing new knowledge. Third, a decay phase. Knowledge is lost faster than it is produced. Replication fails. Citations die. Experts retire without successors. Institutional support shifts. Formats become obsolete, and the loss follows an exponential curve, because the same mathematics that governs radioactive decay governs the dissolution of any population of items with a constant probability of failure per unit time. The growth phase looks like the Enlightenment. The saturation phase looks like the late 20th century. The decay phase looks like what happens when you stop paying the maintenance cost. And the signature, the way you detect which phase you are in, is not in the gross output numbers. It is not in the number of papers published, or the number of patents filed, or the size of the database. Those numbers can keep climbing even during the decay phase, because new production can mask the loss of old knowledge. The signature is in the replication rate, in the citation concentration, in the ratio of disruptive to consolidating work, in the number of living experts per critical knowledge domain, in the fraction of digital references that still resolve to the content they were meant to point to. Those are the vital signs. And the vital signs, if you look at the data, are not good. And I need to tell you more about Boltzmann, because his life is the knowledge decay cycle compressed into a single biography, and the parallels are too precise to be coincidental. He was a large man physically, bushy beard, round spectacles, described by students as passionate and often funny in lectures. He held prestigious positions at the University of Vienna, at Graz, at Munich, At Leipzig, he was not marginalized in the professional sense. He had chairs, he had students, he had publications in the best journals. But the intellectual war with the energeticists hollowed him out. It was not just Mach. It was Wilhelm Ostwald who argued that energy, not atoms, was the fundamental reality. It was the younger generation of positivist physicists who treated Boltzmann's statistical mechanics as old-fashioned, as philosophically naive, as the kind of thing a serious physicist should have moved past. The pattern here is exactly the one I described in the institutional critique. First, it was impossible. Atoms could not be real because they could not be directly observed. Then, when Boltzmann showed that the statistical behavior of atoms could explain macroscopic thermodynamics with mathematical precision, the position shifted. It was not that atoms were impossible, it was that they were unnecessary, an unnecessary hypothesis, a metaphysical indulgence. The physics worked just as well if you described everything in terms of energy without needing to postulate invisible particles. The one thing Boltzmann's atoms could never be, within the professional culture of late 19th century physics, was important. At a meeting of the Imperial Academy of Sciences in Vienna in 1905, the year before his death, Boltzmann gave a lecture in which he described the controversy with a weariness that is palpable even in the written transcript. He compared himself to a man fighting against the current, unable to make headway, unable to convey what he saw so clearly to colleagues who refused to look. He was, by every account, exhausted and depressed. His health was failing, his eyesight was deteriorating, and the recognition that would have vindicated him, the experimental proof that atoms were real, was tantalizingly close, but had not yet arrived. He hanged himself while his wife and daughter were swimming in the sea at Duino. His daughter found him. 2 years later, the atoms he had spent his life defending were confirmed beyond dispute. The K in KTLN2, a constant that encodes the thermodynamic cost of forgetting, bears his name, because the community that had driven him to despair eventually realized he had been right about everything. His tombstone in Vienna carries the equation S equals K log W, and tourists photograph it without understanding that the man buried beneath it built the theoretical floor on which the entire relationship between information and physics now rests, and that the edifice was erected over his grave, not beside him while he lived. The broader pattern of knowledge fragility at the individual level is worth documenting, because it shows that the decay cycle does not just operate on civilizations and on literature. It operates on the knowledge held inside individual human beings, and when those people die, particularly when they die young, the loss can be permanent. Évariste Galois was born in Paris in 1811. By the age of 18, he had invented group theory, the branch of abstract algebra that now underpins modern physics, cryptography, and much of pure mathematics. He tried repeatedly to publish his work. The French Academy of Sciences lost one manuscript. Augustin Louis Cauchy, one of the leading mathematicians of the era, received another and apparently misplaced it. A third was submitted to the Academy's competition and rejected by the secretary Simeon Denis Poisson, who called it incomprehensible. Galois was politically active, was imprisoned twice, and on May 30th, 1832, at the age of 20, he was shot in the abdomen in a duel over circumstances that remain unclear. He died the next morning. The night before the duel, he had stayed up writing, frantically annotating his mathematical manuscripts, scribbling in the margins, "I have not time. I have not time." Those manuscripts sat unread for 14 years. In 1846, Joseph Liouville, finally examined them, recognized their importance, and published them. Group theory, which Galois had essentially invented in his teenage years, had been sitting in a drawer for over a decade while the mathematical community went without it. The knowledge existed. It was encoded on paper, but without a living person to interpret, champion, and disseminate it. It was functionally inert, dead information in a dead man's handwriting. It took Liouville's intervention to push it into the Lindy Tale, where it has survived ever since. Srinivasa Ramanujan, born in Erode, India in 1887, produced mathematical results of such depth and originality that G.H. Hardy at Cambridge famously compared some of them to the work of Euler and Jacobi. Ramanujan had almost no formal training. He worked largely in isolation, filling notebooks with theorems that he intuited without proof, many of which took professional mathematicians decades to verify. He came to Cambridge in 1914, collaborated with Hardy for 5 years, contracted tuberculosis, returned to India, and died in 1920 at the age of 32. He left behind notebooks, and one of those notebooks, a collection of over 600 mathematical formulas, was rediscovered in a Trinity College library by the American mathematician George Andrews in 1976. 56 years after Ramanujan's death, that notebook is still yielding new theorems. Mathematicians are still unpacking results that a self-taught genius from South India wrote down over a century ago, many of which Ramanujan himself apparently understood intuitively, but never proved. The knowledge in that notebook existed for half a century in a state that was neither alive nor dead. Encoded on paper, but inaccessible because no one alive knew it was there, or what it meant. And there is Hypatia of Alexandria, born around 360 in the Common Era. She was the last great mathematician and philosopher of the Alexandrian intellectual tradition. She taught Neoplatonic philosophy and mathematics. She was renowned for her public lectures, and she occupied a position at the intersection of pagan intellectual life and the rising power of the Christian Church. In March of 415, during a political conflict between the Roman prefect Orestes and the bishop Cyril of Alexandria, Hypatia was dragged from her chariot by a mob of Christian parabolani, taken to a church called the Caesareum, and killed. According to the most reliable accounts, she was flayed with ostraka, roof tiles or oyster shells, and her body was burned. Her death is the most cited symbolic endpoint of the Alexandrian intellectual tradition, not because she was the only scholar in Alexandria, and not because the tradition ended literally on that day, but because her murder demonstrated that the institutional infrastructure that had protected scholarship in Alexandria for 7 centuries, the patronage, the political neutrality, the cultural prestige that allowed a female pagan philosopher to teach publicly in a Christian city, had collapsed. The maintenance cost of that infrastructure was no longer being paid, and when the infrastructure failed, the knowledge it sustained became vulnerable to the first person willing to pick up a tile and use it as a weapon. Each of these stories is about the same thing. Knowledge exists in people, on paper, in institutions, in cultural practices. It is always temporary. It is always maintained against decay by the expenditure of energy, attention, political will, and economic resources. And when any of those inputs fails, the knowledge degrades, not instantaneously, not uniformly, but on a curve, the same curve Poinard measured, the same curve de Solar-Price described, the same curve the second law of thermodynamics guarantees. And that phrase, stopped paying the cost, is not a metaphor. It is literally, physically, thermodynamically true. And the man who proved it was an IBM physicist who published a one-page paper in 1961 that most of the scientific establishment ignored for 40 years. His name was Rolf Landauer. He was born in Stuttgart in 1927, emigrated to the United States as a child to escape Nazi Germany, and spent most of his career at IBM's Thomas J. Watson Research Center in Yorktown Heights, New York. And in 1961, he asked a question that sounds like it should be trivial, and turned out to be anything but. Is there a minimum amount of energy required to erase one bit of information? The answer was yes, and the amount is kT-ln2, the Boltzmann constant times the temperature times the natural logarithm of 2. At room temperature, about 300 Kelvin, that works out to roughly 2.8 times 10 to the negative 21 joules per bit. An incomprehensibly tiny amount of energy. But the point was not the size. The point was that it was not zero. What Landauer proved is that erasing information is a thermodynamically irreversible act. When you delete a bit, when you take a system from an unknown state and reset it to a known state, you must dissipate at least kT-ln2 of energy as heat into the environment. Information and energy are linked at the most fundamental level of physics. Forgetting costs something, not metaphorically. Physically, every time a bit of information is lost, entropy increases by at least KLN2. The universe gets slightly more disordered, and that cost cannot be avoided because it is a direct consequence of the second law of thermodynamics. For decades, this was treated as a curiosity, a theoretical minimum so far below practical energy costs that it had no engineering relevance. IBM's own research labs, where Landauer worked, were processing information at energy costs billions of times higher than his limit. Nobody cared about the theoretical flaw when the actual flaw was so far above it. But then people started checking. In 2012, a team led by Antoine Barout at the École Normale Supérieure de Lyon published in Nature what is now considered the definitive experimental verification of Landauer's principle. They used a single colloidal particle trapped in a double well potential created by focused laser beams, and they measured the heat dissipated when the particle was forced from one well to the other. Erasing one bit, the measured dissipation was consistent with kT-ln2. The theoretical minimum was real, and in 2014, Holm and colleagues verified it using a completely different system, nanoscale magnetic memory bits. Actual computer memory, not a laboratory analog. The energy dissipated during erasure was, in their words, consistent, within 2 standard deviations of experimental uncertainty, with the Landauer limit. The universe charges a real, measurable thermodynamic price for every bit of information that is destroyed. I need to stop here and make sure you understand why this changes everything about the knowledge decay story. Because up to this point, everything I have told you about medical half-lives and replication crises and citation decay and civilizational collapse could be explained as a human problem. Bad incentives, sloppy methodology, political suppression, cultural catastrophe, all real explanations, all contingent, all implying that with better institutions, better methods, better preservation, we could in principle stop the decay. We could build a system where knowledge only accumulates and never degrades. Landauer's principle says no. It says that maintaining information in a low entropy state, which is what knowledge is, a structured, organized, low entropy configuration of matter and energy, requires continuous thermodynamic work. The second law of thermodynamics guarantees that any closed system moves toward higher entropy over time, toward disorder, toward the degradation of structure, toward the erasure of information. If you want to preserve information, you have to keep paying. You have to keep spending energy to copy, verify, repair, and transmit it. The moment you stop paying, decay begins. Not because of human failure, because of physics. And the man who built the theoretical framework that makes Landauer's principle possible, the man whose constant K appears in that formula, was Boltzmann. The same Boltzmann who hanged himself at Duino 2 years before the atoms he spent his life defending were confirmed. The K in KT-ln2 is his constant. The S equals K log W on his tombstone in Vienna is his equation. Every time the universe charges its thermodynamic price for forgetting, it does so in units defined by a man who was destroyed by the same institutional forces that destroy uncomfortable knowledge in every era. And the framework Boltzmann built leads somewhere that I think even he would have found disturbing, because Landauer's principle does not just apply to computer memory. It applies to any physical system that stores information, including brains, including civilizations. Every piece of knowledge a civilization maintains exists as a low-entropy configuration of matter. Ink on paper, charges in silicon, neural connections in trained minds, institutional practices embodied in living people. Each of these configurations is fighting the second law. Each of them is a temporary victory against the universe's relentless drive toward disorder. And each of them has a maintenance cost. The paper must be kept dry. The silicon must be powered. The neural connections must be reinforced through use, or they decay. The institutional practices must be taught to each new generation, or they die with the current one. When a civilization is growing, when it has abundant energy and functioning institutions, it can afford the maintenance cost. It pays KT-ln2 per bit, per operation, trillions of times per second, across billions of devices and billions of brains, and the knowledge system expands. But when energy tightens, when institutions fracture, when the supply chains that deliver the right iron ore or the right knowledge to the right people break down, the maintenance payments stop, and the second law collects. This is what connects the Bronze Age collapse to the replication crisis. It is what connects Aristarchus's lost treatise to NASA's unreadable tapes. It is what connects the Antikythera mechanism to the 20% of scientific papers with dead hyperlinks. The mechanism of loss is different in each case, but the underlying physics is the same. Structured information in a universe that favors disorder requires constant energy input to survive. When the input stops, the decay begins, and the decay follows a curve. There is one more piece of physics that puts a ceiling on this that I genuinely did not want to believe when I first read it. It was proposed in 1981 by Jacob Bekenstein, a physicist born in Mexico City in 1947, who did his graduate work at Princeton under John Wheeler. Bekenstein was studying black holes, and he proposed what is now called the Bekenstein bound. It states that the maximum entropy, the maximum information content of a physical region is proportional not to the volume of that region, but to the area of its bounding surface. The formula is S is less than or equal to 2 pi Re over h bar c, where R is the radius, E is the energy, h bar is the reduced Planck constant, and c is the speed of light. What this means is that there is a hard, physical, non-negotiable upper limit on how much information any region of space can contain, not a practical limit, not an engineering limit, a limit imposed by the structure of space-time itself. And when you combine the Bekenstein bound with Landau's principle, you get something that should keep every person who cares about the future of knowledge up at night. A civilization occupying a finite region of space with finite energy can store at most a finite amount of information, and maintaining that information against entropic decay requires continuous energy expenditure at a rate that increases with the amount of information stored. There is a ceiling above you that cannot be raised, and there is a floor below you that is always rising. The maximum knowledge a civilization can hold is bounded by physics, and the cost of holding it increases the closer you get to the bound. Bekenstein himself had a career that mirrors the pattern I've been describing. He proposed black hole entropy as a graduate student, and Stephen Hawking initially disagreed with him. Hawking argued that if black holes had entropy, they would have to radiate, which was considered impossible. Hawking then went away and did the calculation and discovered that Bekenstein was right, that black holes do radiate. What we now call Hawking radiation is, in a real sense, the universe charging KTLN2 for the information that falls past the event horizon. Bekenstein died in Helsinki in 2015 at 68. His bound is now central to quantum gravity and to the holographic principle, which suggests that the maximum information content of any volume of space is encoded on its two-dimensional boundary. The holographic principle, the Bekenstein bound, Landauer's principle, Boltzmann's entropy, the second law of thermodynamics. These are not separate ideas. They are the same idea expressed at different scales. And the idea is the same at every scale. Information is physical. Maintaining it has a cost. And in a universe governed by the second law, the default state of any information system is decay. The civilizations that lost Linear B, that lost Roman concrete, that lost heliocentrism for 1800 years, did not choose to forget. They stopped being able to afford to remember. The maintenance cost exceeded the available energy, and the second law collected what was owed. And the signature of that collection, the shape of the curve, is the same exponential decay that Poinard measured in medical literature, the same curve that Arbesman plotted for the half-life of facts, the same curve that Verster calculated for citation half-lives. It is not a coincidence that these curves look the same. They are the same process operating at different scales. Knowledge decay is entropic decay, and entropic decay has one signature: exponential, always. There is an object in the British Museum that I keep thinking about in the context of this story. It is called the Lycurgus cup, and it was made in the Roman Empire in the 4th century of the Common Era. It is a glass cage cup, about 16 centimeters tall, depicting King Lycurgus being ensnared by a vine, and it does something that should not be possible for 4th century glasswork. When you light it from the front, it appears jade green. When you light it from behind, it glows a deep, translucent red. It changes color depending on whether the light is reflected or transmitted. In 1990, David Barber and Ian Freestone at the British Museum published an analysis using transmission electron microscopy. What they found was that the glass contains nanoparticles of gold and silver, typically around 70 nanometers in diameter, dispersed throughout the matrix. These nanoparticles interact with light through surface plasmon resonance, a quantum optical effect that was not scientifically described until the 20th century. The Romans were manufacturing nanomaterials and exploiting quantum optical effects 1600 years before either concept was formalized. They almost certainly did not understand why it worked. They had developed a craft technique, probably through trial and error over generations, that produced a specific visual effect. The knowledge was procedural, not theoretical. They knew how to do it. They did not know why it worked. And when the craft tradition broke, the how was lost, along with the why. No comparable dichroic glass was produced again until modern materials science rediscovered the principles in the 20th century. That is a 1600-year gap between manufacture and explanation, and it illustrates something about the decay cycle that I think is the most disturbing implication of all. It is not just that we lose knowledge, it is that we lose the ability to know what we have lost. The Lycurgus cup survived as an object because it was beautiful and was collected by wealthy people who preserved it as art. But the craft tradition that produced it left no record. If the cup itself had not survived, if it had been smashed or melted down, we would never know that the Romans had achieved what they achieved. The knowledge would not be lost. It would be never existed as far as the historical record was concerned. How many Lycurgus cups have there been in history? How many craft techniques? How many theoretical insights? How many experimental results existed in civilizations that fell and left no physical artifact to prove it? We know about the Antikythera mechanism because a ship sank in the right place. We know about Aristarchus's heliocentrism because Archimedes happened to mention it in an unrelated book about large numbers. We know about linear B because clay tablets are fireproof and survived the burning of the palaces they were stored in. Each of these survivals is an accident. Each one reveals a lost tradition that we would otherwise never know existed. And for every tradition that left an accidental witness, there are how many that left nothing? This is the deepest problem with the knowledge decay cycle. It is self-concealing. The things we have lost and know we have lost are a tiny fraction of what we have actually lost. The Library of Alexandria's catalogue, the Panarchis compiled by Callimachus, listed works by author and subject. It was itself a form of meta-knowledge, a map of what was known. And it is gone. We do not just lack the texts that were in the library, we lack the catalogue that would tell us what texts were in the library. We have lost the knowledge, and we have lost the index that would tell us what knowledge we lost. Every civilization that goes through a decay phase loses not just knowledge, but knowledge about what it knew. The signature is not just an exponential curve of declining information. It is an exponential curve accompanied by a growing blind spot. The further you get from the peak, the less you know about what was at the peak. And by the time you are fully in the rebuilding phase, the previous peak looks smaller than it was, because you can only see the fragments that survived, and you mistake the fragments for the whole. We are doing this right now with the 20th century. We think we know what was known in 1950 or 1970 because the major papers and the major figures are well documented. But the craft knowledge, the tacit expertise, the unpublished insights, the experimental tricks that lived in specific people and specific labs and were never written down, those are already decaying. The technician who could tune a specific type of mass spectrometer by ear, the machinist who could cut a specific alloy to tolerances that should not have been possible on the equipment available, the programmer who understood a specific piece of legacy code because they had written it in assembly language in 1973, and nobody since has needed to understand assembly in that particular way. These are the modern equivalents of the Roman concrete recipe. They are being lost right now, not in a dramatic collapse, but in a slow, quiet attrition of retirements, deaths, institutional reorganizations, and platform migrations, and the data shows it. The replication rate is falling, the disruption index is falling, the citation concentration is increasing, the digital link rot is spreading, the expert population in niche fields is thinning. Every one of these is a vital sign, and every one of them is trending in the same direction. The direction the second law predicts. the direction the curve always goes. And nobody is synthesizing these trends. Nobody is looking at the replication crisis and the citation decay and the expertise attrition and the digital fragility and saying, these are not separate problems. These are different manifestations of the same process, a process that has a name in physics. It is called entropic decay, and it has a signature, and the signature is visible, and we are in it. And this pattern of knowledge held in single points of failure extends far beyond rocket engines. The problem is systemic, and it is accelerating, because modern knowledge is not just specialized. It is specialized in ways that create dependencies nobody tracks. In 1997, the last person who knew how to repair a specific type of neutron detector at Oak Ridge National Laboratory retired. The detector was still in use. The documentation was on file, but the documentation described what the detector did, not how to fix it when it broke. The tacit knowledge, the sequence of disassembly, the specific torque on specific bolts, the visual indicators that distinguished a repairable fault from a catastrophic one, all of that was in one man's hands. When he left, the laboratory had to reverse engineer its own instrument from a device that was sitting in its own facility, powered on, operational, and unfixable by anyone on staff. Multiply that by every piece of legacy scientific infrastructure in the world, and you start to see the scale of the problem. Particle accelerators, telescope arrays, atmospheric monitoring stations, ocean sensor networks, nuclear waste containment systems, all of them depend on expertise chains that are 1 or 2 retirements away from breaking. The knowledge is not in the manuals. It is in the people who learned from the people who built the systems. And those chains are fraying. And the digital transition, which was supposed to solve the preservation problem, has in many ways made it worse. Because digital knowledge has a dependency that analog knowledge does not. It requires functioning software to be readable. A clay tablet from Mesopotamia can sit in the ground for 5,000 years, and a scholar with good eyesight can still read it. A floppy disk from 1985 cannot be read by any computer currently manufactured. The data might be intact magnetically on the surface of the disk, but the hardware to read it is extinct, and the software to interpret the file format is no longer maintained. The knowledge is there, it is not accessible. And the gap between there and accessible is the gap between alive and dead. The scroll to codex transition of the 3rd and 4th centuries, which silently destroyed the bulk of ancient literature, has a modern analog that is happening right now. Every time a file format becomes obsolete, every time a software platform shuts down, every time a cloud storage provider goes out of business, a scroll to codex decision is being made. Which data gets migrated? Which gets archived in a format that might not be readable in 20 years? And which gets left behind? The decisions are being made by default, by inertia, by budget constraints, by nobody in particular. Just as the decisions about which scrolls to copy into codices were made by overworked scribes in underfunded scriptoria, the decisions about which digital knowledge survives are being made by engineers managing server costs and product managers discontinuing features. And the data on this is specific. In 2014, Martin Klein and colleagues documented that 20% of scholarly references were already suffering from reference rot. 2 years later, Jones and colleagues found that 75% of URI references pointed to content that had changed from what was originally cited. That means 3 out of 4 hyperlinked citations in the scientific literature are no longer reliable pointers to the evidence they claim to reference. The citation is still there. The link is still blue. But what is on the other end is either gone or different. The appearance of a connected knowledge system masks a reality of widening gaps. Bruce DeCarla has been trying to fight this since 1996, when he founded the Internet Archive and began systematically copying the web. The Wayback Machine now holds over 800 billion web pages. It is one of the most important preservation efforts in human history, and it is run by a non-profit that depends on donations and grants. The long-term survival of the most comprehensive archive of human digital knowledge depends on the continued willingness of individuals and foundations to fund it. If the funding stops, the archive degrades. If the servers fail, the copies are gone. The maintenance cost of digital memory is not lower than the maintenance cost of physical memory. It is different in kind, but comparable in scale, and far more dependent on continuous electricity and continuous institutional will. And the irony, the deep structural irony, is that we are producing knowledge at a rate that has never been matched in human history, while simultaneously building preservation systems that are less durable than clay tablets. The growth curve and the fragility curve are both exponential, and they are pointed in the same direction. More knowledge, stored in more fragile formats, maintained by more precarious institutions, with more single points of failure in the expertise chains. A 2022 paper by Chu and Evans that I mentioned, Loss of Sustainability in Scientific Work, published on Arxiv, put numbers on this from a different angle. They measured disruption, a metric that captures whether a paper is reshaping its field or merely consolidating existing knowledge. A highly disruptive paper is one that causes subsequent work to cite it instead of the papers it cites. It redirects the flow of attention. A consolidating paper is one that is cited alongside its references. It reinforces the existing structure without changing it. What Chu and Evans found is that the disruption index across all major scientific fields has been declining steadily since the 1950s. Science is producing more consolidating work and less disruptive work with each passing decade. The system is growing in volume, but not in transformative power. It is, in the language of Kuhn, doing more and more normal science and less revolutionary science. The paradigm-maintaining machinery is getting bigger. The paradigm-challenging capacity is getting smaller. And this is exactly what the decay signature looks like during the saturation phase, before the visible collapse begins. The publications keep coming, the databases keep growing, but the ratio shifts. More repetition, more refinement, more incremental extension, and less fundamental challenge to existing frameworks. The system is not stagnating, it is calcifying. The knowledge base is hardening into a structure that resists its own revision. And if Kuhn was right that paradigms do not reform themselves from within, that they change only through crisis and revolution, then a calcified paradigm is not a stable one, it is a brittle one, waiting for the anomalies to pile high enough to crack it. And now I need to bring you back to the present, because everything I have described so far, the half-lives, the replication failures, the lost civilizations, the thermodynamic flaw, all of it converges on a question that I think is the most uncomfortable question in this entire story. And the question is not whether knowledge decay can happen to us. It is whether it is already happening to us, right now, and whether the signature is visible if you know what to look for. There is a concept in software engineering called the bus factor. It refers to the number of people who would have to be hit by a bus before institutional knowledge of a critical system is lost. If only one person understands how a particular piece of infrastructure works, the bus factor is 1. That person leaves, retires, or dies, and the knowledge goes with them. In 2013, NASA attempted to restart production of the F-1 rocket engine, the engine that powered the Saturn V that took humans to the moon. The F-1 was the most powerful single-chamber liquid-fueled rocket engine ever flown. 5 of them produced 7.5 million pounds of thrust, and NASA could not build another one. Not because the blueprints were lost. They had the blueprints, but the blueprints were incomplete. They captured the design, but not the manufacturing process. The engineers who had built the original F-1s had made thousands of judgment calls during fabrication, adjustments, and modifications that were never written down. Decisions about welding sequence and torque specifications, and inspection criteria that existed only in the heads of the people who made them. Those people were in their 80s or dead. NASA had to reverse engineer its own engines from museum specimens to recover knowledge that had been lost within a single human lifetime. Think about what that means. The most powerful spacefaring nation in history, with the largest engineering archive ever assembled, could not reproduce its own greatest achievement 50 years later, not because the physics had changed, not because the materials were unavailable, because the tacit knowledge, the embodied understanding that existed in living human beings, had decayed out of the system. The bus factor for the Saturn V had hit 0, and nobody noticed until someone tried to restart the line. And the Saturn V is not unique. There are entire scientific fields where the number of working experts globally is in the single digits. Classical Maya epigraphy, certain branches of Pacific Northwest indigenous language linguistics, the maintenance and operation of specific legacy instruments at national laboratories, the synthesis techniques for certain research chemicals where the original developer has retired and the published methods omit key steps that were passed down verbally. There is a 2022 Arxiv paper by Johan Chu and James Evans titled Loss of Sustainability in Scientific Work that quantified something related. They found that the rate at which new scientific papers disrupt existing knowledge, measured by how much new work redirects citation patterns away from older work, has been declining for decades. Science is producing more papers, but each paper, on average, is less disruptive than papers produced in earlier eras. The system is getting bigger and less innovative at the same time. More accumulation in bulk, less paradigm-shifting insight per unit of effort. The growth curve is bending. The decay signature is becoming visible not just in the loss of old knowledge, but in the declining potency of new knowledge. And here is where the Lindy effect provides the final piece of the picture. And it is not the comforting piece you might expect. Nassim Nicholas Taleb formalized the Lindy effect in his 2012 book, Anti-Fragile. The idea, which originated from observations about television comedians at Lindy's Deli on Broadway in the 1960s, is that for non-perishable things, ideas, technologies, books, the longer something has survived, the longer its expected remaining lifespan. If a book has been in print for 40 years, you can expect it to be in print for another 40. If it survives another decade after that, its expected remaining life extends to 50 more years. Survival breeds further survival. The distribution is a power law. Taleb wrote, and this is his exact phrasing, "If a book has been in print for 40 years, I can expect it to be in print for another 40 years. But, and that is the central difference, if it survives another decade, then it will be expected to be in print another 50 years. What the Lindy effect describes is not the population of knowledge. It describes the survivors, the tiny fraction of ideas that make it through the decay, and the mathematics of that survival is brutal. It follows a Pareto distribution, a power law, where a very small number of ideas survive for an extremely long time, and the vast majority are forgotten almost immediately. Euclid's Elements, written around 300 before the Common Era, is still in use, It has survived for over 2,300 years. By Lindy, its expected remaining lifespan is another 2,300 years. Newton's Principia, published in 1687, has survived for over 300 years and will likely survive as the cockroaches of the knowledge ecosystem. They persist through every collapse, every paradigm shift, every civilizational dark age. But they represent an unimaginably small fraction of all knowledge ever produced. For every Euclid's elements, there are tens of thousands of mathematical treatises from the ancient world that are completely gone. For every Principia, there are hundreds of 17th century physics texts that no living person has read. The Lindy survivors create the illusion of cumulative progress because they are the only things visible to us. We look back through history and see a chain of great works leading to the present, and we assume the chain was always growing, always adding links. But the chain is a selection artifact. It is what is left after the exponential decay has taken everything else. Combine Arbsmann's population-level exponential decay with Taleb's Lindy power law survival, and you get the full picture of how knowledge actually behaves. At any given time, a civilization has a body of active knowledge. Most of it is recent and fragile and will be forgotten within years or decades. A small fraction is old and robust and will persist for centuries. The bulk decays exponentially. The tail survives by power law. And the transition between the two, the point at which knowledge either crosses into the Lindy tail or collapses into the decaying majority, is the critical threshold that determines what a civilization retains. And here is the part that I still do not know how to think about. The threshold is not set by the quality of the idea. It is set by the maintenance infrastructure. Aristarchus's heliocentrism was a better model of the solar system than Ptolemy's geocentrism. It was correct, it was more parsimonious, it was more predictive in the ways that matter, and it was lost for 1,800 years because the institutional infrastructure that could have maintained it, could have copied it, taught it, defended it, did not exist. The idea was Lindy-worthy, the civilization was not. Which means that right now, in the early 21st century, there are almost certainly ideas in the published scientific literature that are correct, important, and Lindy-worthy that will be lost, not because they are wrong, not because they will be superseded by better ideas, but because the institutional infrastructure that maintains them, the funding systems, the journal subscriptions, the server farms, the trained experts, the graduate programs, will stop paying the maintenance cost. And when that happens, the second law will collect what it is owed, and those ideas will decay out of the system, just as surely as Aristarchus's treatise decayed out of the ancient Mediterranean. I want to end with a story that connects all of this, because I think it is the most human version of the knowledge decay cycle, and it happened not in ancient Greece, but in 19th century Vienna. In 1847, a Hungarian physician named Ignaz Semmelweis was working at the Vienna General Hospital's first obstetrical clinic. The first clinic was staffed by doctors and medical students. The second clinic, next door, was staffed by midwives. And the first clinic had a maternal mortality rate from childbed fever of between 10 and 20%. The second clinic's rate was about 2%. Women begged to be admitted to the second clinic. Some chose to give birth in the street rather than enter the first. Semmelweis investigated. He noticed that the doctors in the first clinic routinely went directly from performing autopsies on cadavers to examining and delivering patients without washing their hands. The midwives in the second clinic did not perform autopsies. When Semmelweis's colleague, Jakob Kolechka, died from a wound infection contracted during an autopsy, with symptoms identical to childbed fever. Semmelweis put it together. The doctors were transferring what he called cadaverous particles from the dead to the living. He instituted a policy of hand-washing with chlorinated lime solution between autopsies and patient examinations. The mortality rate in the first clinic dropped from 18% to about 2%. In some months, to 0. He had the data, he had the mechanism, he had the results, and the medical establishment destroyed him for it. His colleagues were offended by the suggestion that they were killing their patients. The chief of the clinic, Johann Klein, opposed him. When Semmelweis's appointment was not renewed in 1849, he left Vienna. He continued advocating for hand-washing, became increasingly frustrated and erratic in his arguments, and in 1865, at the age of 47, he was committed to a mental institution by his colleagues. He was beaten by guards. He died 2 weeks later, most likely of sepsis, the infection that kills you when bacteria enter your bloodstream through a wound, the very thing his discovery could have prevented. Germ theory, which vindicated Semmelweis completely, was established by Pasteur and Lister in the years after his death. The knowledge he generated was correct, was published, was demonstrated with data, and was suppressed by the institutional infrastructure of his own profession. It took decades for it to be reabsorbed into medical practice. In the intervening years, an unknowable number of women died from an infection that Semmelweis had shown how to prevent. That is the knowledge decay cycle at human scale. Discovery, resistance, suppression, loss, rediscovery. The signature is the same, whether you are measuring citation half-lives in a database or counting the dead in a Viennese maternity ward. And the engine driving it is not human malice, although human malice plays its part. The engine is the cost of maintenance, the cost of holding a low-entropy truth in a high-entropy world that constantly, relentlessly, without malice or intention, pushes everything toward disorder. Poinard measured the half-life at 45 years for hepatology. Boltzmann generalized it to all factual knowledge. De Soler-Price measured citation decay and documented the Antikythera gap. Kuhn described the paradigm cycle and its permanent losses. Landauer quantified the physical cost of forgetting. Bekenstein capped the maximum information a civilization can hold. Boltzmann built the framework and died before it was accepted. Ventris decoded a 3,100-year silence and died at 34. Semmelweis saved lives and was beaten to death in an asylum. The cycle is real. The decay phase has a signature, and the signature is this. It looks like progress right up until the moment it does not. The papers are still being published. The citation counts are still climbing. The databases are still growing. But underneath, the replication rates are falling. The citation half-lives are concentrating on fewer and fewer canonical papers. The tacit knowledge is draining out of aging expert populations. The digital links are rotting, and the maintenance cost is rising. The surface looks like accumulation. The substrate is eroding. And the universe does not care. The universe does not care about your knowledge, your libraries, your digital archives, your Nobel Prizes, or your grand unified theories. The universe is an entropy gradient. It runs in one direction, and every piece of structured information, every fact, every theorem, every recipe for concrete or steel or Greek fire, every memory in every human brain is a temporary reversal of that gradient, a local pocket of order in a cosmos that prefers disorder. And every pocket has a maintenance cost, and every maintenance cost is eventually not paid. Poignard's 45 years is not a failure of medicine. It is the thermodynamic half-life of a particular type of structured information in a particular institutional environment. Change the environment, change the half-life. But you cannot change the fact that the half-life exists. You cannot build a system where knowledge only grows. You cannot escape the second law. You can only pay the cost for as long as you can afford it, and hope that the things that matter most cross into the Lindy tail before the invoice comes due. And right now, at this moment, there are ideas in the published record that are Aristarchus caliber correct. Ideas that will reshape how we understand reality, if they survive. And they are sitting in a database that will exist for as long as someone pays the server bill. Written in a format that will be readable for as long as someone maintains the software. Understood by a handful of experts who will be alive for as long as biology allows. And the second law is patient. It has been collecting since the beginning of time. It has never missed a payment. And it will not start now.